Hi, welcome to my talk about exploiting chlorophyll fluorescence for building low-cost mowing area detectors. So I'm Nils Rottmann, and these are my colleagues, and I hope you will enjoy my talk. So as our title already suggests, we want to detect the mowing area for autonomous lawnmower, and we want that by designing a really low-cost sensor which makes autonomous lawnmowers really cheap and affordable for any kind of people. So what is the state of the art? The state of the art is a perimeter wire, and the perimeter wire gets buried here at the boundary line. This is really expensive because you need to bury that, and often you need a special machine to do that. And so what then happens is that there is a current flowing through this perimeter wire, and this current induces electromagnetic field, which can be measured by the lawnmower with special sensors. So with the state-of-the-art technology, we need this kind of perimeter wire and also some sensors on the robot. So it's quite an expensive sensor system. And what we propose now is an active low-cost sensor approach, which kind of uses a chlorophyll fluorescence from the lawn. And the idea is to send some light to the grass, which is then, whereas then a part of it resent to as chlorophyll fluorescence, which can then be measured. And how this is done exactly, I will discuss now in the next sections. So let's go over the general concept of our sensor approach. So what we are using is the chlorophyll A absorption and the chlorophyll A emission spectra. So the chlorophyll A emissions absorption spectra is given here in blue and has two peaks, one around 430 nanometers and one around 670 nanometers. And the chlorophyll A emission spectra has one peak and is given here in red. So the one peak is around roughly at 680 nanometers. So what we're using now, we excitate our chlorophyll fluorescence with a consumer LED around 430 nanometers. So this is the yellow line, the consumer LED spectra. And then, based on the excitation, we got then a chlorophyll A emission, which is around 680 nanometers. And we then record or register this emission of the chlorophyll fluorescence using a simple consumer phototransistor. And this consumer phototransistor is mostly in the near IR spectrum. And we plotted here two different phototransistors, one with this spectrum, with this relative sensitivity, and the other has this relative sensitivity. And as you can see, we have here with the green phototransistor, we got here a problem, since the green phototransistor will also see some light from the LED, and this is not really favorable. So we would prefer to use this phototransistor, even if it had not a perfect sensitivity at our required spectrum from the chlorophyll emission. And in addition, we use then a fast pulsing LED to avoid sunlight sun radiation. So to filter then and only see the chlorophyll emission from our pulsing LED, we can then use simply a bandpass filter. So let's come to the processing step for our sensor. So let's start by having a look onto our sensor. So as you can see here, this is a phototransistor, and here's the LED. And on the back side of our sensor, we got the microprocessor, some resistors and so on, and we got here a USB panel, with which we can then connect our autonomous lawnmower to our sensor, or our sensor to our autonomous lawnmower. And the signal paths or the processing steps are the following. We start with the microprocessor. And the microprocessor uses a PWM signal for controlling the LED. which is in a current control loop basically. And the LED sends then an excitation light to the lawn. So this excitation light is basically with a wavelength of 430 nanometers roughly, and excites then the chlorophyll fluorescence. In addition, we have some ambient light sources here, namely the sun, which also excites chlorophyll fluorescence. So what we get back then from the lawn is, on the one hand, the excitation response, which we really want to measure. So this is the chlorophyll fluorescence induced by our LED light. And we got some ambient light reflectance from the sun, which also has IR parts in it, or near IR parts in it. And we got also the chlorophyll fluorescence response from the sun. But we can distinguish between these two signals, because this signal is kind of a DC. It has a really low frequency, roughly around 10 hertz, and this is much faster. We pulse our LED with roughly 35 kilohertz. So we record this then with our phototransistor. So we got, on the one hand, the fast excitation response, so the fast pulsing excitation response, and the ambient light reflectance and chlorophyll response from the ambient light sources. And this is really with a low frequency. So what we measure then with a phototransistor is kind of this signal. So with a high DC in part and really low AC part. And this AC part comes from the excitation response from our LED. So what we do then to get to know our signal is we first use a transimpedance amplifier, then forward the signal to an amplifier, and then to a bandpass filter. And this is really the important part, the bandpass filter here, because this frees our signal of our ambient light influences. So we get then our nice pulsing signal with these rectangles back. And this freed signal we then send back to our microprocessor, where we can detect it and say, okay, we got really our response, or we get really a chlorophyll fluorescence response. So that's the general idea and the general signal path loop for our sensor. And now let's have a look onto our results. And we will evaluate this onto some lawn. So we evaluated our sensor on a real garden environment by trying to detect the mowing area. So marked here with these red lines. And as you can see, we got really distinct features for our mowing area classification, which really allows to use the sensor in an autonomous lawnmower setting. How did we get these results? We put our sensor into a autonomous lawnmower and then drove around the area. You can see here in blue the driving lines. Of course, we detected the position of our lawnmower using a positioning system, a real-time positioning system, but this positioning system has a kind of inaccuracy of roughly 10 centimeter, so that's why it's kind of noisy here. It seems to be noisy. Normally, if we have a really correct positioning system, it would be much smoother. But however, we can see we got here really distinct features, and this is kind of the take-away message. Our sensor works such that we can really apply it onto a autonomous lawnmower to detect the mowing area. So let's come to the conclusion. We designed an active low-cost sensor, which is based on chlorophyll fluorescence. You can see our prototype here on the right side again. So we have here an LED and here a phototransistor. And the idea is to send some light with the LED onto the lawn and get or measure the chlorophyll fluorescence response. We tested our sensor on in a real garden environment, and we showed that our sensor is able to robust and precise detect the mowing area, as you can see here. But however, we required to statistically evaluate our sensor in different lawn environments, for example on really good grass, bad grass, and so on. And we would like to compare it also to the state-of-the-art approach with the parameter wire, to compare how efficiently can a lawnmower mow the lawn with the parameter wire, and how efficiently can it mow the lawn with our new sensor. So I thank you for your attention. I hope you enjoyed my talk. If you like to discuss this in more detail, then feel free to get in touch. Thank you a lot.